My sister told me about it when I was a little kid. And I determined at that moment I would understand what it meant. She said nobody understood it or something like that. Anyway, it's really a thrill to be here in Berlin and participating in this meeting. My talk had a title that sounded rather specific, and I will get to that towards the end of the talk, but I'm putting a subtitle on here. So it's just black hole entropy and vacuum entanglement. So like many of the other speakers, I'll try to give somewhat of an overview of the history of this topic and where it's led us to today. And I will get to a specific new idea about that I had, but it's much more general than that. So we'll start with a black hole. I won't go back to learning about black holes, but I will mention this particular black hole is not spherical because it's spinning. It's a Kerr black hole, and which we learned about in 1963. And the fact that there's an exact solution of Einstein's equation describing that object is absolutely amazing and was an incredible gift to relativity and to physics and science. And maybe the most important thing about the fact that it was an exact solution was that we could analytically recognize that there was a region sufficiently close to the black hole called the ergosphere, where the time translation symmetry became space-like. Because of that, negative energy states were available in the ergo region, and that meant that energy could be extracted, rotational energy could be extracted from the black hole. And that led to the idea of interacting with a black hole as a system that could be exchanging energy, and therefore the question arose, how efficiently can the energy be extracted? And this led to black hole thermodynamics. At least one line of reasoning that led to black hole thermodynamics was that. Another line was simply the worry that came up even with a spherical black hole, which is that a black hole is a great garbage pail for entropy. So Wheeler posed the question to Bekenstein in 1971, what happens if I dump some entropy into a black hole? In particular, Wheeler phrased it in terms of teacups. There are lots of stories about the Wheeler teacups. Apparently the teas in Princeton were a very important part of doing physics. When he poured the tea into the cup, heat was exchanged, entropy increased. But Wheeler said he could conceal from all the world that increase of entropy by dropping the teacup into the black hole. And then the outside entropy would have gone down. And that would violate the second law of thermodynamics if you try to apply it in the region outside the black hole, which of course you have no choice about. If you live outside the black hole, you won't know anything about the inside. So if thermodynamics is only good if you also jump into the black hole, that's not going to be a very useful theory. And the intuition was, that can't be right. There has to be a way to do thermodynamics without jumping into the black hole. So Bekenstein thought about it, and thought about it some more, and realized that if the teacup is dropped into the black hole gets bigger. It's a dynamical object. The teacup has mass, the black hole will get bigger, therefore something about the black hole changed, and Bekenstein proposed that really the important thing that changed was the area, not the mass, the area, and he proposed identifying the entropy with the area in Planck units. The Planck length squared that Joe mentioned yesterday is this incredibly small length squared, and you could say, well, actually, let me get to that in a moment. So Bekenstein not only proposed that this is the black hole entropy, but of course he proposed that this would save the second law if he added it to the entropy on the outside. And he called that the generalized second law. That the outside entropy plus this black hole entropy, which was defined up to a coefficient of order unity at that stage, could not decrease. So in any process, it would necessarily stay the same or get bigger. Now, why did he think area was the right thing to use for entropy? There are a few reasons. One was that he already knew about the area theorem, that according to classical general relativity, the area of the horizon can never decrease. And that sounded analogous to the second law of thermodynamics, that entropy can't decrease. So that was one reason. It's an extensive quantity, and the most important reason is the one that I think most people know the least, are the least aware of, which is that he did an analysis of dropping things into black holes in all possible trajectories he could devise. And he considered both non-rotating and rotating black holes. And he showed that actually, if you try to increase the area of a black hole by the minimum possible amount that you can, taking into account the uncertainty principle of quantum mechanics, and taking into account Einstein's equations and what it tells you about how a black hole grows when you drop something in it, you find that there's a minimum area change, which is actually the Planck length squared. And that minimum is independent of the mass and spin of the black hole. This is a key conclusion from his paper. So he said, according to the information theory interpretation of entropy, the minimum change of entropy, not as an expectation value, but at the minimum by which the number of bits of missing information could change is 1, so the entropy change is log 2. So there's a specific number, basically 1, that should be the minimum. So therefore, since the minimum area change goes like Planck length squared, the ratio of those two should correspond to the minimum definite change of the amount of information inside the black hole. And that's really, for him was the most important reason for identifying the entropy with the area. And I think it was I think it accounts for why he was so confident about this proposal. It wasn't just an off-the-cuff proposal. Well, he tested the proposal of the generalized second law by some thought experiments, one of which is immersing the black hole in a bath of radiation. The temperature of that bath could be controlled. The black hole had an effective temperature because once he assigned it an entropy, then just using dE equals TdS, he could figure out, and associating the energy E with the mass, he could figure out what the temperature was, up to a coefficient of homogeneity. And he found that the generalized second law would fail if the black hole is immersed in a bath whose temperature is colder than its own effective temperature. And that effective temperature he had found was proportional to h bar, and it went like h bar times the surface gravity. An important thing is he didn't know actually at the time that this quantity was surface gravity. He just calculated it from the Kerr metric. But it turned out later it is the surface gravity, which, by the way, I should say, even further substantiated its identification with temperature, this product, because of the theorem that the surface gravity is uniform on the horizon, as temperature should be uniform in equilibrium. Okay, so it failed, but he didn't write his paper saying it failed. What he said was, well, this is an extremely low temperature, proportional to h bar. Kappa goes like 1 over the Schwarzschild radius for a Schwarzschild black hole. So the wavelength of radiation that's colder than that is longer than the black hole size. In fact, there's also an 8 pi squared or something, so it's really big. And therefore, the radiation doesn't just go into the black hole like a laser beam. It scatters off the black hole and usually doesn't really go in. So he said, well, this is dominated by the regime of fluctuations, and somehow the second law doesn't have to hold in that case. So this is the one place he stumbled, because actually the second law has to hold in all cases, and an expectation value of the entropy can't decrease, and it definitely would have been decreasing here. And so what history could have been here plays out in different storybook scenarios. So let me give the first storybook version. Bekenstein realizes at this point that the second law requires, generalized second law, that a black hole radiates at a temperature of order h bar kappa. He notices that it's proportional to h bar, so it's a quantum effect. so it's not surprising that we didn't know about it before. That reminds him that the equilibrium problem for radiation, and more generally, even understanding what entropy fundamentally is, required quantum mechanics. Reminds him that to understand the entropy of radiation required quantum field theory, and therefore he started thinking about quantum field theory around a black hole and realized, of course, a black hole is going to radiate, because even if it's not spinning, it has its time translation Killing vector is space-like inside the horizon, and a quantum field lives both inside and outside the horizon, and so there are negative energy states inside the horizon, and so a black hole will radiate. And that would have been another one of his predictions. It didn't happen that way. Version 2 is that somebody else basically went through that reasoning. It didn't happen that way because it turns out nobody else was paying much attention to Bekenstein. He wasn't taken very seriously yet. So storybook version 3 is that Hawking, who doesn't even believe in black hole entropy, in fact told Bekenstein that it was a foolish idea, is studying something else. He's calculating spontaneous emission from a rotating black hole. Because, as I mentioned earlier, rotating black hole energy can be extracted from it. It had been realized that quantum fields around a rotating black hole would spontaneously generate particles for the same reason. And he was trying to calculate that process of particle creation from spinning black holes, and he discovered that even if the black hole is not spinning, it still emits particles, and in fact with a thermal spectrum, and guess what? It goes like exactly h bar kappa divided by a very specific nice number, 2 pi. So in this storybook version is the real version, as you know. So Hawking discovered that the actual temperature is that fixed the coefficient in the entropy to be exactly 1/4, and it saved the generalized second law. And at that point, Hawking started believing in black hole entropy. So what is Hawking radiation? I already mentioned the reason it's happening is that you can sort of see from this beautiful picture by Roger Penrose, time translation is going up on the picture, outside, and in fact the symmetry is up on the picture inside the horizon also. But just by inspection, you can see that if you go up from this point, you're going in a space-like direction. So that symmetry is a space-like symmetry, so the conserved quantity it's associated with is a momentum locally, not an energy. And momentum can have either sign, so negative energy states exist inside there. And so the quantum field living around this horizon is unstable. The vacuum is unstable, and what happens is that sort of pairs of vacuum fluctuations, which are straddling the horizon, can get peeled apart by the gravitational tidal effect. So think of this as some outwards propagating mode of a field. Since it's outside the horizon, it can't climb away eventually. Inside the horizon, even an outgoing mode falls in. And so this pair, which starts out as an entangled pair in the vacuum, and I'll explain exactly what that means in a little bit, gets peeled apart. And the piece that gets to infinity ends up in an excited state, not in the vacuum, and that's the Hawking radiation. So it's a vacuum instability. I just want to quote, for history's sake, this great quote from Dennis Shum I found to reflect what the reaction at the time was. Hawking's discovery, I should say, was in 1975, I think, or maybe 74. In 76, Dennis Sciama, on the discovery of Hawking radiation, said, in my opinion, Hawking's discovery stands out as one of the greatest advances in the history of physics. And he elaborated, it's a phenomenon whose very existence depends critically on combining the conceptual and formal structures of both quantum field theory and general relativity. Unifying discoveries of such scope are rare in physics, and when they occur, they're likely to lead to a whole variety of fruitful consequences. And then he made comparison with Faraday's unification of E&M, Maxwell's unifying electromagnetism and optics, Einstein unifying gravitation and inertia. and then the profound connection with thermodynamics and the unexpected nature makes it. So, in a way, we're looking back to 76, and how long has that been? 40 years ago. And asking, so what have we gotten out of this at this point? Where has this amazing discovery led us to so far? I would say that arguably the most fruitful of these fruitful consequences is probably, in his personal opinion, ADS-CFT duality. I hadn't realized this until I heard Joe Kolchinsky say this at one point, that if you trace back, how is it that Juan Maldacena actually stumbled upon this amazing duality? It came out of looking at the problem of understanding black hole or black brain entropy in string theory, and it really was directly a consequence of pursuing the mysteries of black hole entropy. But it goes way beyond that. Probably more fruit is to come. And I should also say that I left out a piece of the quote from Shum where he said it's an in principle observable phenomenon. And it is in principle observable, and so far we haven't observed it from a real black hole. But last month it was just announced that Hawking radiation has been observed in an analog black hole. And I want to tell you briefly a little bit about what that's about. So actually, the idea for it goes back to 1980, when Bill Unruh, in his paper Experimental Black Hole Evaporation, made the analogy between a black hole and fluid flow. If a fluid is flowing faster than the speed of sound, and sound in the fluid is swept along with the flow and can't go back upstream. And he said he came up with this analogy when he was giving a colloquium to explain black holes to undergraduates, I think. But he thought about it and realized the analogy is really very good, and that if the perturbations of the fluid, the phonons, are quantized, then the same arguments that led Hawking to the Hawking effect would tell him that the fluid horizon should radiate phonons thermally at the Hawking temperature. So it's been a long time since then, 35 years. There's been a lot of work actually developing that analogy, finding similar analogies, looking into the theory behind it. In fact, experiments have been done on various types, but the first experiment to claim, well, maybe not quite the first one to claim, the first one with really concrete evidence for observing precisely Hawking radiation with phonons that are entangled quantum mechanically inside and outside the acoustic horizon just appeared last month by Jeff Steinhauer, who's at the Technion in Israel. So he says observation of thermal Hawking radiation and its entanglement in an analog black hole. Something amazing about this paper is that it has one author. This is an experiment with a Bose condensate. And most papers in that area, in fact, I think maybe all papers in that area, have multiple authors. And Jeff started out this work with multiple authors a few papers ago. He's been systematically developing his experimental technique. But a few papers ago, he lost the multiple authors because I think he lost his funding. And he's been just going it alone. So this is, if this is true, his claim, I think it's an absolute tour de force, and it would have been a tour de force with a team. But the fact that he did it by himself is really amazing. So, but okay, it should be confirmed, but let me tell you, here's what's going on in the experiment. It's a condensate of 1,700 rubidium atoms. It's in a trapping potential that makes it, it's very confined in the transverse direction. So it's basically a linear Bose condensate in one dimension. And here's a picture of it. He creates the black hole by forming a step potential like that, using lasers to interact with the atomic levels of the rubidium, and it's actually repulsive potential. And he sweeps it from right to left through this linear condensate at a speed of 0.18 millimeters per second. And when he does that, the condensate, because the potential is lower on this side, spills over the waterfall, picks up kinetic energy, and flows back that way. Meanwhile, the step is moving this way. So if you go into the co-moving frame with this step, what you see is a condensate flowing past you and speeding up on the back side. Okay? And that means that actually, if you're a phonon on this side trying to propagate upwards, you can't keep up with the step. Also, the speed of sound changes because the density is lower here because of mass conservation, because it's speeding up. And the speed of sound in a Bose condensate depends on the density also. So this creates a horizon. And then in order to observe the particle creation, he had to develop a technique of optical imaging of the condensate that I think hasn't been done by anyone else at this level. Condensates used to be imaged by turning off the trap potential and letting them just expand. And once they got big, taking a picture of their shape. But he's doing this in situ, locally measuring the density of the condensate after he's created this black hole horizon. So here's a picture of some of his data from his paper. This is a position graph. It's a density two-point correlation function. He ran 4,600 repetitions of this experiment with the same initial conditions and built up the statistics for the correlation function. The temperature, I should say, comes out to be about 1 nanokelvin. That's the Hawking temperature, but it's not quite h-bar kappa because the potential step is so steep that it's shorter than the healing length, which is the length scale on which the fluid description really works for the condensate. So it's in a kind of ultra-high Hawking temperature regime. It would be like a Planck scale Hawking temperature. And it's still kind of thermal, but you don't see the exponential. You just see a 1 over frequency dependence in the emission probability. Anyway, the most important thing here is this black whisker here, and here too. Those whiskers represent the correlation between phonons that have been created on either side of the horizon and are then propagating away from the horizon with definite speeds. And the slope of the whisker is determined by the speed of the phonons on either side of the horizon. And by Fourier transforming this two-point function along this dashed line, he's able to extract a quantity which was introduced actually by Bush and Parentani to diagnose the extent to which the state that this is that's producing these correlations is quantum mechanically non-separable, that is entangled or not. So he could actually measure the quantum entanglement of the phonons. And he claimed to have measured it and found that they're truly entangled, just like the Hawking prediction said. This is really amazing, and if you get nothing else out of my talk, it's already been worth, I think, sitting here to hear about this. Okay, so now let's get back to the bigger picture about what is about black hole thermodynamics. What the heck is black hole entropy? What is it counting? A black hole looks like just a big, smooth, classical space-time. Entropy is supposed to be counting microstates compatible with a macrostate. If we go back and look at the Hawking process and think about the entropy in Hawking radiation, it arises because although the vacuum is a pure state, you're seeing just sort of a half of each pair, and the pair is entangled, so you see a quantum mechanical mixed state for that Hawking phonon in the case of Steinhauer, and so it has entropy. But if we trace it back, it already had entropy if we had just taken into account that we couldn't see its partner on the inside of the horizon, because the horizon is a causal barrier. So there's already entropy here, just tracing over the quantum mechanical degrees of freedom inside the horizon. Now, a horizon of a black hole, and of any horizon, is observer dependent. If you fall through that black hole horizon, unless Joe's right about the firewall, it just looks like any other place in space-time. So let's look for the real resolution of what black hole entropy is in Minkowski space-time. So here's Minkowski space. Here's Euclidean plane. Here's a Minkowski plane. This is all we need to understand the key point. Euclidean space has a rotational symmetry about every point, in addition to translational symmetries. Minkowski space has translational symmetries and boost symmetries around every point. And while rotation takes a point all the way around a circle, which covers the entire, encircles the origin, a boost over here acts just within this triangular wedge. So whatever the vacuum state is in Minkowski space, since it's going to be invariant under Lorentz boost, if it's Lorentz invariant theory, it's going to be taken to itself under this flow. So as an operator, the density matrix for the vacuum must commute with the Hamiltonian that generates that flow. But that's just the boost Hamiltonian. So it's already saying something about it, and further arguments tell us that it's not just any function of that Hamiltonian, it's e to the minus that Hamiltonian. It's a thermal state with respect to that Hamiltonian. And the most complete way to understand this is to actually talk about not the state restricted to that wedge, but the entire vacuum, but expressed in terms of the tensor product of the left and right factors of the Hilbert space of the quantum fields. So we just divide space in half. Every quantum state, including the vacuum, is a sum of products of a quantum state on the left and a quantum state on the right. So in particular, if we take the boost Hamiltonian and look at energy eigenstates of it, labeled by their, some index that labels their energy, and take such a state on the right, take the CPT conjugate state on the left, take the tensor product of the two, multiply it by this thermal-looking factor, and sum over all the energy eigenstates, what we get is exactly the Minkowski vacuum. So this is what it means to say that the vacuum is entangled, and we already see something thermal about it. In fact, to make that completely clear, let's trace over the left-hand side and see what the reduced density matrix is on the right. Then we just square this coefficient, and we get e to the minus 2 pi over h bar. And this is nothing but the Gibbs ensemble for a thermal state at temperature h bar over 2 pi. So that's known as the Unruh temperature, or maybe Unruh boost temperature. If we want to explain why it doesn't have dimensions of energy, that's just because the Hamiltonian generating a hyperbolic rotation has dimensions of action instead of energy, so the temperature has dimensions of action. And this is the same coefficient as appeared in Hawking's calculation, but this has nothing to do with black holes. So to translate between the two, we only need the surface gravity of the black hole, and that has no meaning locally. That's just kind of a normalization factor. So we found the origin of black hole temperature in Minkowski space, and here's the proposal that's natural, is that we also find the origin of black hole entropy in Minkowski space. Namely, this mixed state has a huge entropy. And how much entropy does that have? This idea was first proposed by Raphael Sorkin in 1983 as the origin of black hole entropy, or at least as an important part of it. So we take that reduced density matrix on the right, form the von Neumann entropy of it, and try to evaluate it. In a simple-minded way, we can just integrate the entropy density temperature cubed times the volume. The temperature, this is the effective temperature in terms of that boost Hamiltonian, but measured locally. And it goes like 1 over L cubed, where L is the distance to the horizon. So it would be like, at a point here, take the proper distance between there and the horizon, that's L. 1 over L is the temperature, so 1 over L cubed is the cube. And if you integrate this down to L equals epsilon, you get the area, transverse area, divided by epsilon squared. So it should be dimensionless, it's an entropy. So we get an entropy that scales with the area, it's infinite, in ordinary quantum field theory without a cutoff, but if we put a cutoff on epsilon and the length, we get something that looks similar to Bekenstein's entropy. Now, we can't elect to leave this out. When Bekenstein told us the generalized entropy is the entropy outside of the black hole plus the black hole entropy, this is some of the entropy outside the black hole. Right? It's in the vacuum of the quantum fields that can never go away. So we have to include it. But what about the black hole entropy? Then we'd be double counting. Also, what about the divergence? It certainly is a problematic idea, but on the other hand, it's a completely unavoidable idea. But the problem with it is that it's sensitive to this UV cutoff, which means that most of the entropy comes from whatever physics is making this finite, if there is such a thing. So there is a way to understand this in terms of renormalization of Newton's constant. The hypothesis that goes back a ways, I guess probably the first paper to mention this explicitly is by Susskind and Ugelin, is that you have to understand the total entropy of a generalized entropy as the outside entropy plus the black hole entropy. But there's an ambiguity because both Newton's constant and the outside entropy are cutoff dependent quantities, scale dependent. So we pick a scale and we just count the outside entropy for quantum fluctuations and everything else longer than that scale. And everything shorter than that scale we lump into this Bekenstein entropy term. But it has a scale-dependent Newton constant. And we can actually check that the scale dependence this has to have to coincide so that the sum of these two is independent of epsilon is the same scale dependence that we get from looking at the renormalization flow of scale dependence of Newton's constant. For example, if we take epsilon to be a really long scale, so there's almost no entropy here, we just get we get the Newton constant that Eric Edelberger was talking about today. That's just Newton's constant, and there's nothing but this, and we just don't have to include this. But if we wish, we could always look really closely at short scales outside the black hole, and then we would get a big contribution from this entanglement. That would mean this term must be smaller. But that means Newton's constant must be bigger at short distances, which is true. The effect of coupling and gravity gets stronger at short distances. So this is the picture that I think you have to adopt to understand this origin of black hole entropy as entanglement entropy. It's not a complete picture because we can't just use quantum field theory. Remember, to have a finite total answer, we need a UV regular theory, which just plain old quantum general relativity, perturbatively quantized, is not. So why should the entropy come out finite anyway? Is there any chance that it could? Well, the one thing we left out in that QFT argument was gravity. I just counted up in the Minkowski vacuum quantum field entropy. If we put in gravity, then we look at these correlated pairs of vacuum fluctuations. When they get closer than some critical scale, or cutoff scale, L sub c, eventually the uncertainty principle tells us that the uncertainty in the geometry of space-time due to the fluctuations in energy will make it impossible to tell whether these two fluctuations are separated by a horizon or not. Or putting it differently, the horizon is fluctuating on a scale bigger than their separation. That happens when this length is smaller than the Planck length. So gravity somehow blurs the bipartite division of space into these two factors and tells us that we shouldn't believe in this entropy as shorter than this scale, but this doesn't give a specific mechanism or a way to compute the finite quantity that you get in the end. It just is a kind of consistency that putting gravity in gives you a reason to cut it off. Okay, so that's the first part of the talk in history summary. So now I want to talk about actually a connection between the Einstein equation, which of course, entered that story right back at the beginning, just looking at the structure of black holes and how they interact with things that fall into them. And this vacuum entanglement entropy, and specifically the idea that entanglement entropy is maximized in the vacuum in any small ball of a fixed volume. So I want to first read this arrow from upper left to lower right. I'll try to argue that the Einstein equation implies, in a sense I'll explain now, that the entropy in the vacuum is the maximum that it can possibly be. So first I have to rephrase Einstein's equation. So here's a way to state the vacuum Einstein equation. This is purely classical. In any small ball, and I'll be more precise about that in a second, but just picture a ball in space of a fixed volume, and small means it's small compared to the radius of curvature of space-time there. Any such small ball has the same surface area as it would have had in flat space-time with the same volume. Okay. That's equivalent to the vacuum Einstein equation, as I'll show you in a second. And if you have matter, then actually the area is not the same, but there's an area deficit, which goes, it's proportional to Newton's constant and the energy inside the ball and the radius of the ball. So let me show you, prove those two statements. So pick a point in space-time O, pick a time-like direction, and launch all the space-like geodesics orthogonal to that, and run them out for a distance, proper distance L. And then we get a geodesic ball of radius L. And assume L is much less than any curvature length scale in space-time here. So we're only going to count curvature to the lowest non-trivial order, which means we're going to do a Riemann normal coordinate expansion around that point O. Then we can express the metric as Minkowski plus something times curvature times coordinate increment squared. That's all we need to get the following formula. That if you consider the variation away from flat space as the curvature correction to the Riemann normal coordinate system, the area variation of that ball, holding the volume fixed, which means I'm going to adjust the radius so the volume doesn't change, is proportional to the Ricci scalar of the spatial section generated by those geodesics. I'm doing this in any dimension because I want to keep track of these coefficients to make sure it works in any dimension. So omega d minus 2 is the area of a d minus 2 sphere. D is the space-time dimension. That's the Ricci scalar of the d minus 1 spatial section. And this is actually equal in tensor terms to the naught-naught component of the Einstein tensor of the space-time in this Riemann normal coordinate system. Now, according to the Einstein equation, I just want to point out about keeping these coefficients straight. I could have considered holding not the volume fixed, but the radius, and I would get a similar formula, but with a different coefficient. The ratio of those coefficients is d plus 1 over 3. So it's going to be important that I have specifically this coefficient and not that times this. So something is special about holding the volume fixed, but I actually don't know what. Now Einstein's equation says G naught naught is Newton's constant times T naught naught. And if I plug in T naught, G and T naught naught here, times L to the D. Okay, now I'm going to make another assumption about the smallness of this ball. It started out small compared to curvature. Now let's choose it small compared to any gradient scale in the energy momentum tensor. So T naught naught and G naught naught are basically constant through the ball. I multiply that energy density T naught naught times L to the D minus 1, and I get the energy in the ball. There's one factor of L left over. So we've now concluded that we can state Einstein's equation this way. The area deficit at fixed volume is proportional to Newton's constant times the energy in the ball times the radius of the ball. Now, let's just divide both sides of this equation by h bar g, the Planck length squared, just to re-express it. Then over here we get the Bekenstein-Hawking entropy of this ball. It's not a black hole, it's not a Rindler horizon, it's just a surface around a ball that I chose to look at. And on the right-hand side, I cancel the Newton constant and I get an h bar in the denominator. So now I've expressed Einstein's equation in a way that has no Newton constant in it at all, and it only refers to entropy. Well, on the left it refers to the entanglement entropy across the surface of the ball. And in a minute I'm going to interpret this as another entanglement entropy contribution. But I first just want to argue that this will always decrease the total entropy of the ball. So I can think of that as the surface entropy contribution coming from the area and any other extra entropy that's inside the ball. And let me now argue that I can't put more entropy into the full system. So here's the argument. Here's our ball. Here's a pair of entangled qubits. I'll take one of them, put it in the ball to try to increase the entropy inside the ball. Well, when I did that, I had to localize it inside the ball. So the energy that it must have added to the ball has to be at least, or the uncertainty of it, at least such that delta EL over h bar is greater than 1. However, that was exactly the combination I had here on the right-hand side of Einstein's equation, delta EL over h bar. So this must be greater than 1, so minus it must be more negative than minus 1. Okay, so that means that I decreased the area contribution to the entropy by more than 1 bit, but only added 1 bit to the ball. So in attempting to increase the entropy, I actually decreased it. So there's a basis for suggesting that the entropy really is maximum in vacuum. I could try to put an entire thermal radiation inside there. You don't even do as well as 1 bit. Turns out the best you can do is have the energy as spread out as it can possibly be. You can consider highly entropic systems, like a kind of a particle that has many internal states. That doesn't help either. And so it seems consistent with these kinds of simple arguments to claim that the vacuum entanglement entropy is maximized at fixed volume. Now let's see if we can turn that around and argue it the other way. Suppose maybe that's like a principle. The entropy in the vacuum is maximal. Could that imply